Hi, I'd like to put a further video on example 5.6 with these 4 data point. Okay, so first of all, we see that the questions that we have 20 data in the population, and then we perform 1 in 5 systematic sample of size of n equals to 4 to collect those data. Okay, so if I put it into this way, in an Excel, I hope you can see that clearly, that I have a sample, a population of 20. Okay, so if I list the population into this way, because I'm putting it into 1 in k items. So if I have this, the first item, second, the third, fourth, fifth, the sixth, seventh are of the data that I'm looking at the population. Okay, so those are the household income. Okay, so if I have a random start of the second data or the second household being collected, I obtain 12,100, and then I collect in a systematic way. So the 7th household would be 22,100, etc. Okay, so I have a sample of 4, which is a 1 in 5 systematic sample. So this is only one systematic sample I collected. So I look at the data, I look at the mean. So taking the average of the 4 data point, we have 29,000. So this is my Y bar under the systematic sampling scheme. So if I say that if I don't think there's any trend of the data with the original populations, I would simply assume this is a simple random sampling, and I can use the estimated variance formula under the SRS, or simple random sample equations. So I just look at the SY square within those 4 data points. Okay, so I take the standard deviation, taking a square, and then substitute into the equation SY squared over n multiplied to the finite population correction factor. Then I would estimate the variance, or the estimated variance of the systematic sample, although I am using excuse me, although I'm using the SLS formula to estimate it. That could give me an upper bound for the variance if I assume the original data point doesn't have any trend in it. It's just not an ordered data. Okay, so maybe because of the decimal places, so I do not really end up having this data, but you can check it out for me. So let's look at what happened if I put it into a repeated systematic sampling. Let's look at a half size data point. Okay, so if I repeated this sample into 2 repeated 1 in 10 repeated systematic sample, so that is what I will be doing. Okay, so I put it into 1 in 10 data. So the first start would be the second data, and then because of the k pi is becoming 10, so the next item would be 12, or the second random start would be 7th, and then the next item would be taken would be 17th. So now I'm having a half sample repeated systematic sampling. So instead of having 1 sample, I would have 2 Y bar calculated, or I could have 2 Y bar repeated systematic sample. Or alternatively, if I just look at the original data point, if I repeat it twice, I would simply put 1, 2, 1, 2, 2, find that this belongs to the first data point. So I have my first sample, which is 1, 2, 1, 0, 0, and then the second elements in my first sample would be 3, 4, 8, 1, 0, 0, etc. Okay, so this is how I usually do that to help me to put one systematic sampling into the number of repeated systematic sampling. So let's say if I want to put it into, or if I have more of the sample sizes, if I want to put it into 3 repeated systematic sample, so I would put 1, 2, 3, 1, 2, 3, 1, 2, 3 to separate into the repeated systematic sample. Okay, so now I'm trying to put it into 2 repeated half sample systematic sample. So the first sample, I would have this data, and the average is 23450. The second sample, would be 22100 and 47,000. So I would have 2 y bar. Means of means is 29,000. You can see that it's actually the same as the original data, because if you imagine in reality we only collect one set of systematic sample, but because of the calculation we just flip it to be a half sample repeated systematic sampling, so that we can have the variations of the y bar to estimate my variance. Okay, so in this case we can calculate the sy square between these two, and then substitute into the formula to find the estimated variance, okay, for the half size estimated variance. So or we can use the formula that we mentioned, looking at the difference between the two y bar, taking square divided by n multiplied to final population correction factor, we can find the estimated variance. Again, like I said, we can see there's a substantial reduction of the estimated variance. So I would say that SRS estimated variance is actually overestimating the true variance under the systematic sampling. Okay, all right, so let's look at the differences method. Okay, so successive difference is like the previous example, so I'm not going through that. I like to look at the collapse differences. Okay, collapse differences is like there's two data, I look at the difference, and because I'm using collapse differences, so the differences would be any non-overlapping data, so I would only be able to collect two differences. Okay, and differences square, summation of differences square, and now I would divide it by the number of the data that we collected. Okay, so that becomes our the S square is 124,420,000, and substitute that into the formula, we can find that the collapsed estimated variance and the successive differences per estimated variance, they are both conclude that there's a substantial reduction in the estimated variance. So again, we would say that the variance approximation from the SRS does indeed overestimate the true variance. Okay, there exists a trend in the population of the increasing trend. So if we look at the data itself, or we can plot the 4 data point, we see that there's a substantial increase of the data. Although the data point 4 point is not big enough, then we are to increase the or to improve the estimation, it will actually better to collect more data point. Okay, so the next section will be the sample size determinations. I'm not going to do very details in this, because what I'm trying to say is that under the repeated systematic sampling, we can always relate the standard error of the point estimate within the multiply to the significance factor 1.96. That must be always less than equals to the bound of error that's being required, and then we relate it with, put around with the formula, we can find the sample size needed to achieve this bound of error for the y bar under the repeated systematic sampling would be equals to this equation. Okay, and again for the proportion, we simply replace that as y bar square over ns by p times 1 minus b divided ns minus 1, and for the bound of error, for the total, replace that bound of error b by the bound of error b pi over n for this substitution. Okay, so again, sample size determination under the repeated systematic sampling is showed is applied using this formula. Okay, so that's it for the systematic sampling. Again, I would say that I would emphasize that under systematic sampling, what you need to know is that the distribution of the population, if we see that as a substantial trend, increasing trend, descending trend, periodic trend, if we use a systematic sample of the weights of collecting the sample, we can achieve that within the sample we collected, that we collect the heterogeneous characteristics within the cluster or within the sample. So that could be a superior sampling scheme than simple random sampling or stratification sampling scheme, because this is one kind of the cluster sampling scheme that we would achieve a smaller variance estimate. Okay, so I hope you enjoyed chapter 5 on the systematic sampling, and then later on we will move on to chapter 6 on a more generic cluster sampling scheme. Okay, good luck.